actually look at the diversity of springs in biology. So here's a tree of life, and everywhere on this tree, I can tell you an animal that stores elastic energy. For example, there have been studies that have shown that bacteria store elastic energy in their flagella. This is an ATP synthase. There have been studies that have shown that the ATP synthases of archaea use elastic energy for their pumping mechanism. Elastic energy has been studied in Venus flytraps and in the hyphae of fungi. There have been studies of elastic energy in scallops, in the mantis shrimp, in the legs of cockroaches, and in the stingers or nematocysts of jellyfish. Right? There have also been hypotheses of elastic energy being useful for hagfish and sharks in terms of their skin, allowing really rhythmic, efficient side-to-side motion while they're swimming. Of course, there's the bullfrog tendon, or in case just frog tendons in general. There's been studies showing that elastic energy is important in that, and also in the tongue projections of other reptiles. And also in terms of birds, there have been elastic energy studies done in terms of single feathers and also whole wing structures. And of course, we can't forget the poster boy of elastic energy storage, the red kangaroo, and its runner-up, the human, right? So I just put this up there, and I just want you to take a second to really appreciate that elastic energies are widespread, not only across the phylogeny, but also across size ranges. So it's really important to really understand what unifies this diversity, to study what unifies this diversity in terms of the elastic biomechanics. So even today, even though I'm going to be focusing specifically on mantis shrimp and bullfrogs, something to keep in the back of your head is that what I'm really trying to get at are the biomechanics of springs that are more complicated than just a single spring, and the springs that are connected directly to muscle. Right, so even though we're specifically going to be looking at mantis shrimp and bullfrogs today, keep these schematics and these ideas in your head as we go through the rest of the talk. All right, so that was my brief outline of brief intro of how bioelastic systems are analyzed. And we're gonna move more towards specifically to mantis shrimp to ask the question, what is the mantis shrimp spring? And specifically address this question, where is energy stored in the Aspera spring system? So you might be wondering, and again, we're gonna be working towards getting to this level. Right, so you might ask yourself, well, what is a mantis shrimp? And what's a Aspera mantis shrimp? So here you can see that they're the eyes, antennules. The rest of its body is actually in the sand, so you can't really see it. But I just wanted to show you what these animals do. So that was a fish that was going by. These larger Aspera mantis shrimp strike at evasive prey, and that happened really quick, and you couldn't really see the animal. So I just wanted to put this cartoon up here so that we can understand. So all of this, probably back here, was hidden in sand. You're not seeing that. And to give you a sense of size, we've had species we've had individuals of the species get to about a foot long in the lab. And so what I really just want you to focus on is this appendage here, the striking appendage, and you can see little hints of little spines. It's a lot easier to see in high-speed video, but just keep this whole body, this whole animal in your head while we look at a high-speed video of it. So again, here's the eyes and antennules. It's a sideways facing animal. You'll see it come out this way, grab it. Grab the shrimp that's up here. And again, this is slowed down, but there you can really see what the strike looks like. It's full extension, wraps around, and catches it. It's pretty cool. Now, keep in mind that this was a larger mantis shrimp. This also occurs in mantis shrimp that are smaller, in spears that are smaller. So to give you a sense of scale, this is an eardropper, right? And so this little mantis shrimp is tiny, but you can see the same sort of stereotypical reach out strike. It's pretty cool. All right. So then we get to this question, is there a spring in spears? Right? And again, just to remind yourself, we're starting here at the very base, we're working up our way on a triangle. Is there a spring? So one way that you can figure out if there is a spring, right, is again to look at the power. The other way, or another way that you can do it is actually to look at deformation. And the reason why, just to show an example, when you have a spring, in order to store energy in that spring, you have to compress it. that spring has to deform, there's shape changes, right? So as you can see, as this is compressing, there's deformation. So if you find a biological structure that deforms prior to movement, that's pretty good evidence for at least hypothesis that energy is being stored in that structure. So in case of the mantis shrimp, I'm putting this back up, we want to look for deformation in the striking appendage, and specifically we want to be looking in the maris. So here I've just outlined the entire striking appendage. It connects to the body at this point. But really, what we're looking for is there deformation in the maris prior to striking? And so this study compared a small spear and a large spear. To give you a sense of scale again, these scale bars are 10 millimeters in both pictures. So this one's tiny compared to the large spear. And what this study found was in the small spear, definitely yes, that the maris deforms prior to striking. The large spear, however, they found no, that there was no evidence for deformation in the maris whatsoever. And so this led to the conclusion that large spears don't store elastic energy. But I left 3 little dots down there because I really want to make sure that we understand what the question is asking. And it's that, does the maris deform before striking? So large spears don't store elastic energy in the maris. It's still possible that these animals could be storing elastic energy in other structures. And what could those other structures be? Well, we've already seen the maris, right? But internal to the maris is a tendon known as the epididymal. It passes through right here. And so the actual mantis shrimp appendage represents a system of 2 connected structures, the maris and the epididyme, which looks something like this. Now I'm going to take a quick little side note. This is not that important in terms of the story, but I think it's important to really understand that this is a simplification. And I really want to talk about the maris for just one quick second, which is that I found in my first chapter of my dissertation that the maris actually behaves like a multi-component system, meaning that if you look at the maris itself, it in itself appears to be a connection of springs. So our nice simple example that looks like this, of one spring connected to another spring, actually looks something more like this. But for the purposes of this talk, and I'd be happy to talk about this with you afterwards, or you can check out that paper. But for the purposes of this talk, I'm really going to be black boxing this into a single spring and ask whether or not the epididyme is capable of storing energy or if it deforms prior to striking. All right, so we move on to the next question, which is what is the spring in large spears? And here we have 2 structures, right, connected, the maris and the epididyme. So what I want to say here is that if you have 2 systems that are connected together in series, the structure with the lower spring constant stores the most amount of energy, right? I could show you a mathematical proof, but I'll save you from that. There's a lot more math coming later on. And I'll just put this image up here as a visual demonstration, right? So when you have 2 structures that are connected together, they experience the same amount of force, right? Which is represented by this dotted line. So they'll always be experiencing the same amount of force. But the structure that has the lower spring constant, right, which is indicated by this lower slope here, will have more elastic energy, which is the area, right? So if they're all going to the same force, if you have a lower slope, you're going to get more energy per that same amount of force. I mean, that's sort of like a surrogate for my mathematical proof of why that's true. But this is really cool because this allows us to just go in and test these structures, the maris and the epididyme, and measure their spring constants and see which one is lower, right? The one that is lower will be storing more energy than the one that is higher. So how do you measure the spring constant? Here's an image of a materials testing machine, and this was back at UMass. My desk area was back here somewhere. And I really wanted to put this picture up here because that tiny little dot right there is a mantis shrimp maris, right? To show you a schematic of what's actually happening, there's this metal box, right? This metal box that the mantis shrimp maris was attached or epoxied into. The box itself was connected to an actuator, this thing right here that was able to move the entire box upwards. And what I did was I fed a wire through the appendage, through the box, and clamped it down, so this acts as a rigid point, right? So if you have the box that's moving upwards and this being a solid point, it compresses the maris, right? And so I did this for many mantis shrimp, but a new thing that I wanted to do for this chapter really, right, to get at the material properties of mechanical properties